Okay. So what's the problem we actually want to solve? Well, I'm going to define big U to be U of x comma t and the derivative of U of x comma t. Okay, and I'm going to put, for whatever reason, I'm going to put an I there. So what we want to do is we want to construct a mapping so that we take U at 0, which is U of 0 comma t, I and t is U of 0 comma t, and we map that to, well, I'll just call this big U of comma t. So that's the operator we really want, right? Take some initial condition and it maps it forward, and that solves the time dependent problem. Sorry, you're right. Yes, sorry. Okay, thank you. No, not the same thing. All right. So that's the operator we want, right? So let's write down the system of equations. And what we've got, if we look at it, is we've got U is equal to U of x comma t. So if I take the time derivative of that, I'm going to get dtu x comma t multiplied by I, and here I'm going to get I dt squared. All right. What's that? I have the left. Sorry, no, you're right. Okay, excellent. Okay. Now, all right. So we can write this as this operator acting on U. And I've introduced this I here. Okay, and the reason for that is just because like we write I e to the IKT. I want this operator here to be self-adjoint. So this is all just kind of nonsense at the moment. It's just a language, right? So what we get is we get U of x comma t is equal to the exponential of minus I times this operator. One times everything on U of U. So all this notation is something, but this is the operator we want. That's right. Yeah, exactly. Yes, correct. So, and it's not like I've made all this stuff up, but this really was studied. It's not necessarily a numerical method, though, right? I think that's one of the things that kind of so. All right. So that's our that's the operator that we want to understand. Okay, so what I'm just going to show something for a second here. So here we go. So what this is a numerical solution. So what I'm going to do is I've got 3 cylinders, 4 cylinders here. I'll cut them out, and I've got some initial conditions that look like that lump. I'm going to let it go, and we're going to calculate the time dependent. It's not a natural thing to want to solve the initial value problem in a lot of ways because it doesn't fit the experimental paradigm and all of this stuff. But that's the problem we're going to solve. So I'll show you what the solution looks like. Yeah, but U. You're displaying it. It looks beautiful on my computer, unfortunately. But yeah, I've taken. It's just my problem. I don't want to solve some random scatter like that's somebody else's job. I'm going to solve for a circle. It's a bit easier, right? Here. And then down hard scatter it here to here. And you get The interesting thing about this problem, which you can't really see perfectly here, is that it produces a very strong mode that's trapped inside. It's not, and that's what the singularity expansion method that we're going to try and connect these two in a second, right? So this is the solution to the problem, calculated, and I'm going to show you how I calculated it. Okay, so it's a numerical method. All right.
So just GEM and SDM.
This is the singularity expansion method. So on the right-hand side is the projection onto the single. This is the one-dimensional solution. Column 2 is the solution to the problem, and this is the solution calculated for it. Okay, with probably 1,000 values or something like that. All right. Yeah. They were called A and B prior to that was one of my dramatic changes to the talk. I'll just see if I can show something. Just show another movie. I love these movies. And that they are quite, I think that what Bruce said, that they're great for storytelling, is really true. So it tells the story of where we're going. So this is some, again, it's playing very poorly here thanks to Zoom, but this is a plane wave pulse coming in and hitting it like that from infinity. And then I've had it at this angle because if I came straight on, I wouldn't excite this mode and the symmetry. And then this is the, so this is long-term, the solution, you'll see that. You get complicated scattering here from this problem. This is actually much easier to calculate than the solution before. All right. All right. Okay, so and then all the ways have gone, the settles down to one mode that are oscillating down. So actually, one of the ways to solve that problem challenge is building very trapping. It's surprisingly strongly trapping any group of cylinders really strongly trapped. All right. Okay. Well, this one, I'll show one more movie here. So this is 9 cylinders. So there's the thing starting at the initial condition running out. So the thing with the 9 cylinders is kind of interesting because what happens is you get 1, 2, 3, 4 modes feeding together, and then it decomposes into the ones that are in phase and anti-phase. You can get a kind of weird effect when it starts peaking here, then it shifts around the array or still be trapped. It's strange behavior from it. So in this case, the projection, the basis will have dimension 4. It may not follow that particular the symmetry I impose might have excited all 4 of them. But you can see here these ones are moving together, but it will shift over time. Okay. So it's a practical kind of numerical method and to solve the time-dependent problem. You can compute it. All right. So let's go on here. If I blank this, I can go on to the board. All right. So Larry says that this is a semi-group, a second group, which can go forwards and backwards in time symmetry. Because now we're in the dark. All right. I never shadow. Just going to talk on the black. All right. So what we've got to do is understand this this operator a little bit. So I have it written down up here, but let's assume that because it's a main name like omega, right? So the energy is the integral over omega of the time derivative of u squared. That's the energy, right? So, and since that's a preserved quantity, so we can immediately derive an inner product. Okay, which is the integral of, and then we go IDT in 1 times IDT U2 conjugate plus the x U1 from the U2 conjugate. Okay, so that's why do we need this in a product? We only need it for one purpose, which is to show that this operator here, this operator here is self-adjoint. And well, I suppose we need it for two things. We also need it because this is going to define how we project when we do write down our solution. Okay. I should have written on the underneath for the first there. I can't raise it because it's in down. Yeah, okay, you're going to zero. You learn, I'll learn something. Okay, so imagine if I said here, I take this operator, 0, 1. I don't want to do this because I'm going to get it wrong and you guys will think I'm an idiot. If I do this, then when I get up here, what am I going to get? I'm going to get the first component is going to be this. I'm going to get d by d. This. I've got to be careful here because these are wrong. Choose right. We're going to get the first component is going to become the I. I wrote the second component at the end there. The first is not helping us out, but that component there will be actually just U1 multiplied by the Laplacian minus the Laplacian or something, right? And multiplied by I equals U2. And this one here will be. So you don't have to do that, but you've got these big U's and all that. Which represent U and IDT, right? So you've got little U's. But little U's are the components of it. So like U1. Yeah. Increasing the R. Which is very good. Yeah, two components. Somehow this thing here is swapping them around, isn't it? Right? So it's taking the top and shifting it up, this operating, and it's taking the Laplacian of this and moving it down. So where we had the T of U1, we get the Laplacian of U1, and where we have gradient of U1, we end up with the gradient of I UT. What's that? What you bring the your energy for a fine wave will be we're not allowed to find waves. Forget that. It's got to be in it too. So that's fine. The initial condition, everything is all in on the edge, but yeah. Okay. All right. You can sort of believe me here. If I can shift this over to here, once, right? By Brent's here, and I'll get a gradient acting on here, and I can shift it over here and get Laplacian, right? So you sort of, it's believable if I haven't actually shown it that I can swap this over inside this thing, right? So it's self-adjoint, right? I can swap it over inside the energy in a product. All right. So, all right. I'm going to rub this off and just start writing in the bottom. I think I can press that. Yeah, the Brian, rub it all off. Someone should have told me right at the start. You know? All right. So, what does it mean that it's self-adjoint? It means that the eigenfunction, the spectrum's real, right? So we solve the okay, I need to make blue. All right. So that's how equations are solved to find the spectrum of it. So what does that turn out to be? If you think about this, it's going to be All right. So the evolution operator is some operator whose spectrum is exactly the single frequency solution. So sort of lead back to where we started, right? So the single frequency solutions are the form the spectrum of this operator. All right. So what does that actually mean? What we're going to do is we're going to build a new Fourier transform where these are the bases that we transform with respect to instance, right? Okay, so associated with this eigenvalue problem, the spectrum is continuous, but the spectrum doesn't live in the space L2, it lives in some extended space. So the UN of, I'm going to write it as x comma omega. So that's the solution. What? Single frequency solution. And so it's actually a bit more complicated, right? Because for every spectral point, we get a solution that depends on the end of the I and theta. So we've got the frequency, and these are the frequency domain solutions of this problem, right? You have to stand all the different plane waves that can come in, all the different plane waves that can come in. So we've got this index n and this index omega, and it's asymptotically either j and e to the I and theta. So that's the incident wave plus the scattered. Yeah, so it's the circular wave, yeah, and infinity, right? So you could well, that's the incident wave, if you like. So you're going to have, in the far field, you've got that plus the scattered. Yeah, okay. All right. So what do we do next? I'm trying to build a practical way of solving. You just seen I've solved the wave equation. I could do those full factors with it. So how could I do that? All right. So the first thing is this, and this is a little bit eerie, I think. Union of we want to define this. I'll call it omega 1 and omega 2. So this, okay, so this inner product, which is my, remember how I wrote this down, it's the integral of it. I've rubbed it out, but it's you know, some integral over the domain, omega domain, like something like that. So what? Yeah, you're right. Okay, so yes, there's an index on medium as well as on the number. Okay, so well, what happens is, think about this, when you were trying to do this computation, this thing goes out to infinity, it's just a giant mess. So, and these functions here consist of all that incident wave plus all the scattered waves. But this thing here is just equal to the integral over R2 of, now I've got to be a little bit careful here, but I've got omega and k being equal. So it's perhaps unhelpful here that I've got k rather than omega. Because my omega is equal to k. So here we go. So I'm explaining to you. We've got j is omega j so what I've got to multiply this by some constant in the front here, but what I'm doing is I'm going to plug the formula for my integration over this region, all of it cut out into the, I'm going to say that this must normalize exactly the same as if I just integrate over R2 of just the incident wave.
Use the that, and then
Yes, you're in it, sorry. Now, I've got to, what I'm going to have is I'm going to have a gradient acting on that, right? And the gradient acting on that. Plus I'm going to have an I times, I'm going to have an I equals T. The time derivative is just omega because of that. This is a big step. So basically, but you can think about it that we know that this thing here is going to equal, just from our knowledge of the continuous spectrum, it's going to do delta NM from delta omega 1 minus omega 2. The only thing we're missing here is the normalizing factor. But in this sense, you can just think about it, the thing has an infinite energy, but all the infinite energy comes from this part of it. The scattered energy is just going to be finite. So this allows us to calculate what this normalization is. So this same normalization happens for these functions of all the scattering as would happen without all the scattering. With respect to, I've got I'm going to either the I and theta, either the minus I and theta. I'm missing that here, right? Sorry, yes. It's a physical space, R, the L, and theta. It's not omega. No, it's a physical integration of the physical space. So energy is an integration over E. It's over the physical space. I don't write it down. What's that? I punctured it, no. I can get rid of the punctured domain. And, right? And I know from Brentwood and Stephen that gaining the KR of omega 1 on J, omega 2R, the R, that's equal to something when you're thinking of the constant, right? I know how these normalize. So I can calculate this normalization coefficient here. And yeah, of some complicated function, all the scattering. Yeah. So you want to throw when I normalize it, yeah. Let's go back a second. Yeah, this is critical to the whole thing. You need to know about no, it's not this problem self-adjoint. We know that these functions belong to the continuous spectrum of the operator, right? So, and they have grouping self-adjoint. Yeah, when you do the green theorem, yes. So when I took the thing over, I showed that when I moved it from here to here, I used the boundary condition. We know this is delta NN, delta omega 1, delta omega 2. We don't know what was normalization is. It's quite hard to work that out. So there's a theorem that says that essentially that you can normalize it by getting rid of the bit you cut out of the domain. So that gives you the nice simple domain and throw away all the scattered parts and only have the incident wave. And you can just use formulas that you know about the equal function. Why is that true? Because it's like, okay, like I was interested. Yeah, I go there, right? What is the answer there? 2 pi or something, is that right?
Maybe you can get the definition of the generalized function, right? You can say, so the process to the data and we will take consider the generalized function and then we normalize.
Yeah.
Right?
Yeah. I think that's right, yeah. But if I decide to go, if I cut a bit out, if I go from minus infinity to, you know, I cut a bit out, so to get rid of it, and I go from minus infinity to minus 1, and I go from 1 to infinity, it's still got to be equal to that. Then I remove that back. So it's something like that. If you think about all the energies that all the energy is infinite and all the infinite energies have infinity. So it doesn't know anything about the scatter field anyway. All right. So this is one of the things that's confusing about it. And I don't when I came, I sort of discovered this stuff myself a bit. And what I found was and I worked it out. And then by a very long and circuitous argument, I got the normalization by some process. And then the general theorem pointed out by Prof. All right. So we're good to go though, because what we've got, we're going to solve u of x comma t. That operator we wrote down. Okay? So we write this as the integral from 0 to infinity, minus infinity to infinity. So, that's omega. And then the sum from unity to minus infinity to infinity. I'll put the first and then I can just take the inner product at when t is equal to 0. I'm going to have when t is equal to 0, like u naught is the integral from minus infinity to infinity. Yeah, oh, you're right. Okay. So that's my u naught. Then I just take the inner product of u naught with respect to u of yeah, u of x comma omega prime, say, right? And then I can end up with an expression that f of omega, which is equal to the inner product of u naught divided by the factor of. So it seems kind of crazy in a sense that what I've done, but it's very similar to how you solve the wave equation. So you start out with the initial condition, u naught, then you find the coefficient Fn of omega through this inner product, and then you calculate it back. Yes, it is. 100%. Yeah. What's that? No, they're the solutions of the single bridge together. You calculate the UC matrix. Yeah. So you calculated the U. Should be at that. Yeah. You can have. What's that? And yeah. And yeah, you got that. All right. So one of the really important things to observe is that the way you calculate FM is that you form a giant matrix, which consists of all these UN of this gamma omega. There's a lot of, there's two, it's harder to see this in 2D. I want to do the 2D problem because the 1D just seems too trivial. But when we form a matrix, we can just run the n, and we can run the x's, you know, and convert them from an array into a matrix. Does that make sense? So we form this giant matrix here, right? Where the columns are the x, and the rows are the omega and n. Okay, so imagine just if you've got every solution for n equals 1, 2, 3, 4, 5, and all the omegas, you just form a giant matrix out of that, right? You have to truncate the omega, yes. You have to separate, you have to write them discretely. Yes, that's right. Yes, that's correct. So your omega is discrete. So see the fast order extension, we'll great example of how that works, right? It's not a problem to do that, right? Okay, so this FN, sorry, cat is some giant matrix, which maybe I'll call it UN as a matrix multiplied by the initial condition, multiplied by U naught, right? And then when you look at this expression here, this sum and this thing, you're going to sum up constants of this matrix here. So it's the same matrix appearing again that you multiply when you calculate your x comma t, then it's not exactly the same matrix. It's like the harmonic, the conjugate transpose matrix multiplied by Fn with an e to the I on the known as I on the t thrown in the middle. So, and this is just completely mirrors what happens for a self-adjoint matrix, right? So if I have a A is right to the side, right? A is self-adjoint matrix, then we can write A is equal to or let's go e to the I, right? Then A is equal to some projection matrix, e to the power of I come from diagonal matrix and time, and then multiply by this conjugate, right? So, and exactly like for a self-adjoint matrix, you form the p's from the eigenvectors of the matrix, right? But I think it's really important to see that here. It's something you can touch, right? There's a self-adjoint matrix, then and so it should be due to the time table, right? When you want to do that to a self-adjoint matrix, you find the eigenvectors of the self-adjoint matrix, you form the matrix from them, and then you multiply by these one thing, and maybe get an adjoint here, similar like this. And then you multiply it by the diagonal part. And it was a matrix that has one vector of 1, 2, 3, 9, 10. Our function is ultra simple and it has the complex spectrum the whole line. So the time, if they're going to the numeric solver, is actually, once you've got that solution that you calculated for its frequency, you just basically form this giant matrix and just multiply it out. So all those simulations that I showed you are just these matrices and multiply. Now, and one of the weird things about this thing, the numerics of the whole thing, is that you start out with U naught here, you know the initial condition, and you plug it into this horrendous formula, and then it spits out U at 0. So the method is the most least accurate at t equals 0, which is a pretty weird feature of it. And so you actually know you've kind of everything's working if you can pull out of the whole thing what to feed into it. And then you run it forward in time. And it doesn't, it's not a time thing, it just allows you to immediately do everything in time. Just like here, if you made a mess with this, then you wouldn't get the identity, you know, or something that is easy and go to right or something, you made a mistake and missed something. All right. So I'm gonna so
I still don't understand what the function you and the total and harmonic.
yeah.
For
but it's some way. So it's a bit more complicated than that. But it's not too complicated. Yeah, that's right. Well, you've already got it. If Stuart solved these problems, right, the frequency and ID, pull the giant matrix and solve the time domain by multiplying them out. It's as simple as that. You can directly. And so one of the things that I should say here is that I think the mapping is the most important thing. The most important object in math is the mapping, not the functions, but how they give a mapping. And so our frequency domain solutions form. The reason it's important is they form the mapping that takes us from the now into the future. They're what the mapping is composed of. So that operator that takes the time solution now and moves it forward, that's the fundamental operator, but that's built from the time harmonic solutions. So those time harmonic solutions are giving us that mapping. What?
When you go to the much easier to grab the instant wave away from the separate time.
Yeah, that's because you can add some positive.
Yeah. If you're far away from the scatter, you neglect the scatter wave there as well.
Yeah. All right.
Well, this is very general then, for any scatterers that have boundary data which makes it self-adjoint.
Produce the energy, yeah. Any dimension, yeah. I've generalized it into a few different ways, but where the energy becomes more complicated, to say there's some elasticity, some kind of elasticity built in. All right. So I'm going to write this down. It's important.
About terminology, simple frequencies of random variables type harmony.
Yeah, it's I'm pretty sure it'd be hard to I've got this terrible thing where I'll muddle the noun, so I'll say dinner instead of breakfast. And it happens in more familiar situations, right? The family. But the children love it. But and my mother had it as well. It's got a name, it's genetic, but I always made fun of her as well. It's like, the children that get it. Yeah. They form the map that solves the your comma your moves to your so the solution that takes the initial data and moves it forward, that map is constructed from the single frequency solution. So I think that's why if calculating the single frequency solution is really all we have to do. Why it's so fundamental, even though you can't shine the laser beam forever. I want to just quickly talk about this SEM method. Just touch on that a little bit. So, singularity is anything with it. It's easier to do this. I reckon it's easier to think about this with matrices. But when you solve this with a T matrix, what you get when you solve it, you get a matrix times some vector is equal to a right-hand side. You always end up there, somewhere with your code, whenever you're solving it. And the matrix depends on the frequency, and this S can depend on the frequency. I'm not going to use X here, I'm going to use A. So that's the basic structure of how we solve these equations. And what we do is my use of X omega. If you look at the structure of this, it always looks like this. It's an inner product of A with something, some other vector, and therefore G, which depends on X, the position X. So you calculate the A, so for example, you represent it with some outgoing waves and vessel functions and all this stuff, right? If you want to calculate this is really that was the structure here. And when I say in a product, I kind of mean multiply these together, right? It's a vector. So I'm thinking of it, you know, using maybe notation we don't want. So what we end up with is this U always has the structure of some operator inverse omega multiplied by some matrix F of omega, some vector S multiplied by something that depends on the S. So like this is how you sum up you've got all these Hankel functions, you've got to sum them up. So what you do, you know, this is the basis of Hankel functions, you want to go at some point, sum them up. That's what you do, you take them in the product. So the general structure of the solution always winds up at. When we solve that solution, when I solve the equations that I showed you. Now, this is a discrete version of this operator here. This is where, I think this abstraction here confuses that no other people. Well, it's a discrete version of that operator. But because this is the real operator driving our whole equation, right? It's just trying to mean that it's but if you start working with it, you've got to solve, you've got to start with TU equals AU, and you've got to take all the class transforms and get the TU equals AU plus U. Sorry, yes. And then you've got to solve, so therefore we've got the U is equal to A minus S inverse on U naught, and then you've got to try and do a form with the contour and integrate around it. And you start to begin to understand how you unpack something like that. But I don't think you need to worry about that because we've got something so concrete as matrix inverse. And we know that the matrix is we know that what happens is this M inverse of omega naught is singular. Or omega naught complex, but near the real axis. So what happens then is that M inverse of omega naught acting on the F of omega is equal to it's equal to some vector xn times or maybe okay? Times some constant. But the x naught is an eigenvector at the minute, so we don't really need the constant. But in the end, so you can see what's going to happen. If this inverse has a 0, then it's going to be dominated by that. And we can take that multiplied by G, but then reduce the function. So we're going to end up with what are kind of like the eigenfunctions of this operator, the discrete spectrum of this operator. So you're going to you can sort of define this U naught of x comma omega naught. So it's an eigenfunction of this, which is given by x naught multiplied by the G of x. So you can, if you want to go and try to find this, and that 0, that track mode that I showed, bouncing up and down. What's that? Yeah, that's a very good question. Why does that go away? You really got to go through that step, and I don't have time to do it if you go through that function, but it will come out when you integrate around it. You just calculated the eigenvector of the matrix. You just want that eigenvector associated with singularity, right? Maybe I can explain that. Let's
It would be something like omega minus omega 0.
I've got the TU equals AU, right? And then I can write the solution as this is the sum of either the lambda n t times the I index of x in u, right? So this is a matrix, right? This is some constant AN, right? So the xn's are the points where A minus omega n is singular. Sorry, I'm thinking. I think, sorry, m times omega is equal to, I've got this slightly wrong. This is what it's n times omega n is 0, right?
Just like the version of the Laplace transform,
Yeah.
but for sheer, in the here, and the formula level base, and then you got
Yeah. Yeah, sorry, yeah, that's sorry. Yeah. Yeah, but you're right. But this, yeah. The all right, yeah, I agree. This is, I should have this as some kind of there's a bit of handwriting here, it's not quite right, yeah. But the solution is going to blow up. So we want to scale out the blowing up part. Put the x in there and see. Yeah. All right. And so that's how you calculate the solution that I showed you on these movies. You know, we go back to this movie here. And so, yeah, I'm just trying to show the movie again, and then we'll just finish there just to explain what happened. So on the right-hand side, I've taken all of the solutions, played very smallly, unfortunately, but you imagine there's like 1,000 solutions. I've taken that initial condition, I've multiplied it by the big matrix, I've multiplied it out, and over here, I've taken that initial condition, and I can take the product of that initial condition and just with the eigenfunction like through here, and then I just project it on and get a single free mode solution. And the long-term behavior matches that. But so it's only because it's highly resonant. If it was just a single circle, it could work terribly because the scattering frequencies don't really have any. It's only when you create. So this idea of the singularity expansion method only you sort of understand these highly resonant states. So you've got the very consistent mode.
So something at this kind of new answer that you this problem for say J0 is the right?
Yeah.
Then you do J1 equals the I phase or J1 equals minus I phase, so
Yeah.
then you keep going. How many of those do you have to do?
That's the problem.
Yeah.
I'll probably end up being at the end of the fine, and the frequency is probably 100. So get 1,000. So then you've got to discriminate and get two functions. You've got 1,000 by 1,000 matrix. It's a bit of a nightmare. I could do I'm running this calculation. I stored that on my computer. That's like a gigabyte. I've got to calculate that and it just runs away. And then do the integration. It's a bit of a programming. It's not a trivial problem to program by any means. Like if you go down in the next level into the code, like, because you've got to use the finite element basis and then you use some problems of finite element to help you integrate. You're going to discretize discretizing that space is a bit of a noise. Yes, that's right. So in Meylan, I think your idea was going to talk to you about how to. But at the heart of it, it's just this matrix is multiplying out once you set it all up. And you can solve for all the different initial conditions that become. All right, time to stop there for sure. So there's a lot of questions. I didn't get onto some of the problems about what where we don't know, because the lots of difficulty, especially with this thing here, it's much easier to do this in the frequency domain, but when you come back into the physical domain, what these mean and what they're associated, what the operators are, because you've got this near compactness of this operator, you're approximating with some radiation boundary conditions, there's all kinds of stuff, lots of paths you can take. And this, the stuff that, formalism is definitely well understood by people. Whether they've used it as a computational method, I don't know. And whether it's, but it's
just assume that you have simple poles.
No. But you do have to assume that this dimension of you can easily get double poles, but when they have a 9 case, there's a symmetry there that's going to make one of those poles double, so it's got 2 eigenfunctions associated with it. Okay. So therefore it's not a yes, and there's definitely a branch point in the object plane, yeah. And so the longest time behavior of the system wants to be this kind of, eventually it comes to rest in the p to the minus in the branch. Some really strange result like this. That's right. Yeah, the most persistent transient term, yeah.
The whole idea of for your transform, right? It's very clear that you could represent any solution to an initial value problem as some frequency weighted function times your frequency solution. That's what the Fourier transform is all about. So that you can do the initial same model, right? The method of doing that, right?
Correct. Yeah, that's a good way to think about it. I think that's a good way.
Yeah, exactly. So you can always do that, but the question is what is happening for a different problem and not unknown. So you can tell that the fail.
Think about how you say. And then it's the real part of that or something, right?
Yeah.
You don't actually need to go to optimize it. So we know that's true. The question is how to choose the end to reproduce that pump right at the start. And then the thing that's so, if you want to do this calculation, you're going to have to take this matrix and multiply it by this vector. What I've shown you is to find the Fn, you've got to take the initial condition and multiply it by the transpose of that exact same vector, plus a little bit. Right? So actually, this thing is, that is kind of amazing. I'm not sure. Yeah, but that's the point of it. So how do you choose the Fn so that this is a matches your initial condition? When you've already got it, once you've built then you can do it. But I think the thing is, in the end, I think people don't want to solve the initial gravity problem. Like I said for myself, it's all you make pictures of it, it's not a practical problem. Everything comes back to these single frequencies, which is probably all you need. But I think one of the reasons they work is they ask all the questions that they are mapping, but fundamentally, this is the actual problem that you can approximate the solution from these single frequencies. But the way that the person seems to tune it to be almost one frequency, they want to think of it from infinity, and then usually what comes back to that frequency. But you could interrogate, you could get more sophisticated in things like you could take a couple of pulses down, feed it in, and then see how long it takes, measure as it comes back, and that will probably tell you a whole lot, and it'll actually tell you everything about the system.
This whole crisis is some analytic situation that you're complex and you're not very fast, right? And this is much very possible. It's right, the rate of decay.
Yes, that's right. No, it's been very expansion. Right. If you put 9 of them together, for symmetry, you'll be like plus plus, minus, minus, and then the rotation of that. So you'll end up with two frequencies, but there'll be omega 1 will be 1 plus 0.01 time. It'll be much more persistent as well. It's going to be expressed. It's going to mean how you're going to, but the frequency, the actual oscillatory frequency will remain the same. The decay will be slower than time.
Well, the difference about the generalized approaches, when you don't know the kind of frequencies, that's direct, making the self-adjoint, but by automatic self-adjoint, but you take the part of the time.
Yeah, I'm not sure.
Delta minus whatever.
Yeah.
Minus omega squared, right? Then you can omega is real, but then you can do that's
Yeah, correct. Yeah, exactly. Yeah. Yeah, that's a weird feature of them. Yes, they grow. So you've got here's your initial condition, and then you've got the thing that oscillates and grows like that going out. And you integrate the product of those two. So as long as it's compact, it's fine. But you don't, but the function you integrate with is from the adjoint space, not from the same space as well. But it is, so that is a weird feature of them, that they grow to infinity. But that makes sense because imagine you've got this growing wave traveling this way, and you're standing here, you'll see a wave going, you see the wave oscillating and dying. So it appears to decay, right? It's only standing here. So it sort of makes sense, but it's very counterintuitive. It doesn't seem right that you can do that. Yeah, and back with Valerius, you've got minus Laplacian as self-adjoint, which is positive. But the problem is that you end up with, in the theory, if I gave you the theory that you end up with the square root of that operator, which is a bit annoying. If you're happy with that, then you can do it. You can actually do it without going to the double space. But you end up with like you end up instead of having either the I, A, and T or whatever, you get cos of the minus. Yeah, the square root of minus the Laplacian. I think that. Yeah, that's right. Yeah, you take the sign of the correct. Well, I think that's a different stuff. You can do it like that if you want. Yeah.
For theory, you can start with this, but for numerical implementation, this other approach.
I'm an old Russian professor at Auckland University, Boris Pavlov. I spoke about these approaches.
It ended up in New Zealand.
Yeah, that's right. That's why I'm doing this, because I meet him. Yeah, he's a character, right? Yeah. And I said to him, yeah, no. He's we should, I should have put a picture of him up because it's all come from him. Yes, like all of it. And he said to me, I asked about the two different approaches. You know, use the other one always. But yes, he doesn't like this problem finding stuff.
What's the infinite array? I could imagine it being easier and not something that I should do much more.
Yeah, that's the only question out of 10 that probably was possible. But yeah.
Have you tried to?
Have you got an origin to find the infinite way?
Right, yeah. And you get rid of the continuous spectrum. If you go doubly,
yeah,
the single line array.
Well, you've got, if you have a pass band and stop band, the continuous spectrum means you cut up like that, isn't it? it could be done, I think. There's lots of ways. I don't know,
Should make your array larger and larger. Being what you get to, you know, any kind of, you should be tending towards something, or is this become too horrible to talk about what gigabytes worth and they're 9 in your.
Well, what's really strange is that if you have a very close resonance, the solution in frequency space does something like that, right? So you need a huge number of frequencies here. That becomes harder and harder to compute. You need more and more. So it's actually, it becomes harder for this method to work. It needs, you know, it needs to go just to try to work out breaking points, but it's hard.
What I did in favor of the same one.
Because it's more natural to compute, isn't it? Why does-
It's because it is the schematic.
Yeah. I think it is natural. Yeah.
Yes, but
you know, yes, that's right. Yeah, that's right. Nothing you would, yeah. That's right. Yeah. That initial condition, right, you can move the up. So that initial condition, right? Yeah, it's like a miracle.
This to know how the organization is. I know what to fight.
Yeah, no. And also for the mental functions, you now have to work because you can look up the formula in the book. So that's what makes it so easy, yeah. But you're right, for the best, you know, we now have to normalize that.
You have a non-linearity.
No, that's right. And then even complex numbers just go, throw that idea out. Because they never, don't ask me why, but any nonlinear problem is never some complex number or.
But you know, there's non-linear evolution equation, which when, you know, they use the inverse scattering method, which is essentially the mapping which gets you into the linear scattering problem, and then you propagate it in time.
Yeah.
Doing your problem, that I don't think there are others trying doing it using your approach. So maybe there is some thinking of that.
Yeah, you could work out how to, if you could think about how to get that left here for some system that's tuned into this problem.
That's right. Yeah. But still, the deep
It's all along those lines. It turned out to be really hard. But yeah, because they end up with, this comes from, the theory comes from the Schrodinger equation. There's a really interesting history as well, which is a beautiful, we'll end on this anecdote. The Russians will appreciate it. Some guy wrote the paper in Russia explaining the genesis of this idea at least in 1953, and in 1960 it was more or less translated. Someone actually, I guess the guy did a great service because he read and understood the Russian paper and he translated it. But all the references start with that. The guy translated the Russian word. And there's other papers that's forgotten. Like,
But that is, someone could remember the name of the question.
I don't know, I'm trying to remember the name. I think it's like Pozov. Yeah. But Akiva, I could remember the name of the other guy, you're right. It's like Akiva. But yeah.
Maybe we should thank Mark again.